Hi everyone and welcome to Data Engineering. So in this video for statistics, we're going to cover large and small sample confidence intervals. Now if you guys find these videos helpful, don't forget to leave me a thumbs up and as always, to subscribe. Alright, so before we get into confidence intervals, there are two terminologies that we need to know. The first is the population parameter. So this is a single value that describes a characteristic of an entire population, such as the mean or the standard deviation, for example. Now the population parameter is typically calculated from a sample, but it's meant to represent the entire population, although it won't be that accurate. Which leads me to the confidence interval. So the confidence interval is an interval or a range in which the true population parameter lies for the entire population, given a certain probability like 95%. So as an example, let's say we were trying to measure the average height of all Asians. Now, obviously, it's impossible to measure every single Asian person on the planet and obtain their heights. But what we can do is we can take a sample of Asians. So let's say we have a sample of subjects, subject 1, subject 2, subject 3, all the way down to subject 10. And for each of these subjects, we measure their height, h1, h2, h3, all the way down to h10. And using these heights, we can actually calculate a mean height by adding all the h values together and dividing by 10. So this mean height would actually be the population parameter. I'm just going to call that PP for short. And this is calculated from a sample, but meant to represent the average height amongst all Asians in the world, although it won't be that accurate. Now, using this mean value, we can actually calculate a confidence interval, CI for short. And the confidence interval will give me two values. It will give me a lower bound and an upper bound. And what this means is that the true value of the mean height probably lies somewhere within this interval with a 95% probability. And we can change this to maybe 90% or 99% depending on how stringent we want the confidence interval to be. So the true value for the mean height of all Asians in the world lies within this interval, statistically speaking. Right, so when actually calculating the confidence interval, there are two equations we can follow based on if the sample is a large sample or a small sample. Now the difference is the large sample considers the Z statistic, which is Z alpha over 2, and the small sample considers a T statistic, which is T alpha over 2. In both cases, right there over here, X bar represents the mean value, sigma is the standard deviation, and N is the number of subjects or the number of data points. So you can consider a sample to be large if N is greater than or equal to 30, and this follows the central limit theorem. Likewise, if the number of data points is less than 30, then the sample is considered small. To apply the small sample equation for the confidence interval, the samples also have to be selected at random, and they have to be parametric or normally distributed. So just to sum up, for the large sample, we consider the Z table or the Z statistic, and for the small sample, we consider the T statistic. Now, if you're looking at the Z statistic, you can just do a quick Google search for the Z values, and you'll actually get a table that looks like this. So your alpha is the probability with which you want your confidence interval. So for example, a 95% confidence interval or a 90% confidence interval. Alpha over 2 is simply the alpha value divided by 2, and Z alpha over 2 can be obtained from the Z statistics table, and the values are just given here. So this is just a snapshot I picked up from online. Comparatively, for the T statistic, you'll have to look at the T table, and again you can get a copy of the table online through a simple Google search. One thing you would need to know when using the t-table is that it follows a degree of freedom, and this degree of freedom is actually n-1, which is the number of data points minus 1. So let's look at a few questions. Alright, so the first question is for a large sample confidence interval. And this question follows a transportation company which wants to estimate the average or mean number of unoccupied seats per train journey over a year. So the goal is to estimate mu, which is the average number of unoccupied seats, using a 90% confidence interval. And we've even been given some values. We have the mean, which is 11.6, the standard deviation, which is 4.1, and the number of data points, which is 225. So roughly this would look something like this. We would have the journey. So we would have the first journey, the second journey, all the way down to the 225th journey. And for each journey, we would have the number of seats which were unoccupied. So for example, 2 unoccupied seats, 4 unoccupied seats, and maybe the last journey had 7 unoccupied seats, something like this. And what they've actually done is they've calculated the mean of all these values, and that's x bar, which is 11.6. They've calculated the standard deviation, which is 4.1, and we know that there are 225 data points. So if we want the confidence interval, we can directly apply the equation. So the equation is x bar plus minus z alpha over 2, the standard deviation sigma divided by the root of n. So sigma we have, that's 4.1, n we have that as well, that's 225. We have x bar, that's 11.6. What's left is to find z alpha over 2. Now we know the probability of the confidence interval is 90%. And what that would look like is something like this. So let's say this was our distribution. And let's say we cut the distribution at 2 equal tails. The area over here, which represents the most normal region, is 90%. And the remaining areas over here and over here would sum up to the remainder, which would be 5% each, to make a total of 100%. So in essence, alpha in this case would be 100 minus 90, which is equal to 10%. And of course, alpha over 2, okay, I'll write that over here. Alpha over 2 would be equal to 10 divided by 2, which is 5%, or 0.05. So we want z alpha over 2, which is z 0.05, or z alpha, which is, well, this is 0.1. And what you can do is you can go to the table for the z statistic, and you can pull that value up. So if you just go back to the previous slide, the z value for an alpha over 2 of 0.05 given an alpha of 0.1 is 1.605. So this is the z statistic that we are interested in. So let's go back to this equation. Continue with using a different red color. So our confidence interval, I'll just say CI, would be 11.6 plus minus 1.645. Let me just double check that value. Yeah, that's right. Into the standard deviation, 4.1, divided by the root of 225. And if you solve this, you should get something that looks like 11.6 plus minus 0.45, which leaves me with the interval. So I had lower bound, that's 11.6 minus 0.45, which is something like 11.15, and the upper bound, which is 11.6 plus 0.45, which is 12.05. So if we were to interpret this, what this means is that considering a sample of train journeys, the number of, or the average number of unoccupied seats is 11.6. But if we want the true average of unoccupied seats, considering every possible train journey for this particular company, that true value should lie somewhere between this interval. And that is what the confidence interval shows, the true value of the population parameter. Alright, so the next question looks at a small sample confidence interval. So this question has two parts. The first part is to estimate the true mean skidding distance along a forest road with a 95% confidence interval. So we have a stretch of forest road and we measure the skidding distance at different points along this road, and we want to find the true mean skidding distance given a 95% confidence interval. And the second part is that a worker claims the mean skidding distance is at least 425 meters. Do you agree with this statement? Yes or no? Now we're even given some values. We're given the mean, the standard deviation, and the number of data points. So roughly what this study would look like is we have a forest road and we measure the skidding distance at different, let's say, sections along this road. So section 1, section 2, section 3, all the way down to section 20 because we have 20 data points. And for each section we measure the skidding distance, and let's say we have something like 300 meters, 320 meters, and all the way down to just say 480 meters. And we take a mean of all these values, and that's x bar, which is 358.45. We then have the standard deviation. I'll use the symbol S because it's a small sample, and that is 117.82. And we have n, which is 20, which is the number of data points. Now again, you can directly apply the equation for a small sample confidence interval, and that equation is x bar plus minus. Now we consider the t statistic, so that's t alpha over 2, the standard deviation s divided by the root of n. So again, we have x bar, we have s, we have n. All we need to find is t alpha over 2. So in finding t alpha over 2, you would need the t table, which you can find online, but I have a copy of it saved, so I'll be using that. And the first thing you'll need is to actually calculate the degrees of freedom, which is n minus 1, which is 20 minus 1, and that's 19 in this case. Now let's have a look at alpha. So alpha is 100 minus the probability, which is 95%, which is equal to 5%, which is equal to 0.05. Therefore, alpha over 2 is equal to, of course, 5 divided by 2, which is 2.5%, and that is 0.025. So if we had a distribution that looks like this, and we cut the distribution at the tails, then this region and this region would be 2.5% each. So 2.5 actually represents a single tail, so I'll just say one tail, while the value 0.05, which is alpha, represents a two-tail value. Right, so you can find the t-tables online, but I'm going to jump to that over here. So I have the t-tables, and I'm looking for 0.025 on one tail or a single tail. So here's my one tail values, and this is 0.025, this value over here, which matches 0.05 for two tails. The left-hand axis shows the degrees of freedom. So I have my degrees of freedom as 19, so I can actually just highlight this. And the value I want should be this value over here, which is 2.093. So that means my t alpha over 2 is equal to 2.093. I can now go ahead and formulate the equation. So x bar would be 358.45 plus minus 2.093. This is the confidence interval. The standard deviation, which is 117.82 divided by the root of 20. And if I solve this, I should get a confidence interval that comes to about 303 and 413 approximately. And what this means is that the true mean skidding distance lies within this interval of 303 and 413 meters. So with that, let's jump to part B, which states that the mean skidding distance is at least 425 meters. Now 425 is beyond the confidence interval. It's out of the confidence interval. So this is unlikely because the true mean cannot lie beyond the confidence interval. So the answer for part B is simply no. Right, so let's also look at how to find the confidence interval on SPSS statistics. So I'm using the same example as earlier. I have the skidding distance and I have 20 data points for different values of the skidding distance. Now, if I was to find the confidence interval, all I need to do is go to Analyze, Descriptive Statistics, and click Explore. Choose the variable, that's skidding distance. We're only interested in the statistics. I'm going to go to Statistics and ensure that the probability of your confidence interval is what you want. So in our case, it's 95%. Click Continue and click OK. So you would get your descriptive statistics. Here's the mean value, which is 358.45. You have the standard deviation over here, which is 117.81. And it also calculates the confidence interval, which is the lower bound and the upper bound. So approximately 303 and 413. Alright guys, so that's it for this video on large and small sample confidence intervals. If you guys like the video, don't forget to give me a thumbs up. And hopefully I'll see you all in the next video.